Okay, just continuing on. So, if we're looking at the number of routes, this is actually another application of combinations. It also kind of helps you understand combinations a bit better. And it'll lead us into a really nice pattern that is going to help us do some calculations. Um, One of the situations that we're going to use combinations for is number of ways to travel through a city. So imagine you're traveling through town, want to know how many ways there are to travel 4 blocks south and 3 blocks east. To save time, you'll only go south and east. You're not going to go backtrack. At each intersection, you ask how many times to get to that intersection. So you're kind of starting here, and then you're going to go down to the bottom right here. And so we say at each intersection, how many ways to get there? And so if you think about it, there's only one way to get there, here, and there's one way to get here, and there's one way to get here, and here, and here, and here, and here. Because you can only go straight. Straight. There's no turns or anything like that. You can just get one way on each intersection. Then the next kind of guy right here is here, and if you can think about how many ways to get there, you go one, two, and so the number there is two. And to get here, we go one, two, and three, and so that number would be three. And then we can go one, two, three, four, and so that number is four. And then this number here is kind of similar to that one. It's three. This number here is similar to this one. It's going to be four. But then you say like, okay, you start to get the pattern and say if there's 3 ways to get here and 3 ways to get here, then there must be 6 ways to get here and 10 ways to get here. 4, 10, 20, 5, 15, 35. And so you kind of get the hang of it, and you realize that this is actually a pattern that we've seen before, and it's actually Pascal's triangle. And this 35 is actually, we're going to kind of see where that number comes from. So there's 35 ways to get to the bottom right corner. So now Pascal's triangle is created in the same way. So here's bless Pascal, and so where do combinations come in? Well, let's think about the problem in a different way. So instead of saying, all right, the number of ways to get to each intersection, what you can do is you can actually say, well, how many roads am I traveling? So if you call like each like block a road, so or blocks, we can go 1, 2, 3, 4, 5, 6, 7. So there's actually 7 different lines, and you'll notice that no matter which path you take, there's actually 7 different lines. And so what we're going to do is choose out of the 7 lines that we're going to travel, we're going to choose 1, 2, 3 of them to go east, or choose 1, 2, 3, 4 of them to go south. If you do that, 7 choose 3 or 7 choose 4, you actually get the 35. And you actually kind of figure out, well, there's 7 choose 3. It's just going to be, that's all the decision we have to make is the 7 that we're going to go, or the 3 that we're going to go east. And so we actually solve the question as 7 choose 3 or 7 choose 4, and they're both 35. The nice thing about this is actually like you can see that like it really doesn't matter if you go north, if you choose the south ones or the east ones. They're actually the same thing. And you might have noticed this from the last example with the soups, is if these numbers add up to the 7, then they're going to be the same number. There's 35 ways to go through the city, and so we've kind of connected that idea. If you look at Pascal's triangle, here's like the 35 here, and so you can see, take a look and see if you can find what the numbers mean and what they're doing. Pascal's triangle helps us to understand the nature of combinations, allows us to calculate many combinations without having to go to a calculator. If you go to the 7th row, which is actually the number with the row 7, because this would be row 0, and you go the 3rd number, this is number 0, 1, 2, 3. This is 7 choose 3. This is 7 choose 4, 7 choose 5, 7 choose 6, 7 choose 7, 7 choose 0, 7 choose 1, 7 choose 2. And it also helps us to understand that like why these two numbers are the same, or why 8 choose 2 is the same as 8 choose 6. Or any other numbers, and like you kind of get this idea of Pascal's triangle. So here's a multiple cases example. favorite pizza place orders 8 toppings. This is going to be like one of our big idea questions where this question is actually going to relate to a lot of other questions. So how many different ways can you order a pizza? Probability in this type of example relies on the fact that combinations of toppings are randomly chosen. So if we did a probability question, it's kind of like a really fictitious problem. But the question really does become more important when we start talking about like combining chemicals, combining drugs in a lab, combining like for treatment, combining chemicals in a lab. So like that's where it really does become more important. And so pizza is just kind of like a friendly way to introduce this type of problem. Um, your favorite pizza place offers 8 toppings. How many ways can you order a pizza? To answer this, like you're looking at multiple cases. So you can actually take a one top and think about all the favorite pizzas that you have, or how many like different kinds of pizza you can have. And so a one topping pizza, now it doesn't say that, but like let's assume that you have to have one topping. Um, out of the 8 toppings, we choose one, and so it's 8 choose one. Out of the 2 toppings is 8 choose two, 3 toppings 8 choose three, and so on and so on. And eventually you actually like figure out that you can get them all of these ways. You could do 8 choose 0 too and have a no topping pizza, but the total number of ways are like 8 choose 1 all the way to 8 choose 8. And so the question is, are you going to sit here and calculate all those? Or are we going to use Pascal's triangle? Pascal's triangle, if you look at it, if you add up the rows in Pascal's triangle, you get a nice like pattern. And so we actually need the 8th row. So we want 8, 28, 56. We want all these numbers. There's 8 choose 0, 8 choose 1, all the way up to 8 choose 8. If you add up the rows, so the numbers in each row, not only are they doubling each time, but you're getting the powers of 2. It also works nicely that the exponent's the row number. And so 2 to the 8. So the 8th row of Pascal's triangle is actually 2 to the 8. The 7th row is 2 to the 7. The 6th row is 2 to the 6. So you get 256. But you don't want the 1. So if you want to lose like the no toppings choice, again, you maybe want that. But depending on the question, we can lose it. If we want to subtract 1, so just 8 choose 1 all the way to 8 choose 8, we do 2 to the 8, which is the entire row, and subtract 1. So a probability question would be, what's the probability of random pizza is pepperoni? And so there is 255 ways to do the 8 topping pizza. But then like it's actually easier to think about the indirect method because it's not much different than the question we just did. So A prime is all pizzas without pepperoni. So you just imagine that instead of having 8 toppings, you only have 7. And so that's like the cases for that would be similar as 7 choose 1 all the way to 7 choose 7. So you're choosing all the other toppings other than pepperoni. And that's the 7th row in Pascal's triangle. And so if we subtract 1, we lose 7 choose 0, we get 127. And n of a would be the 128. So 255 minus 127 would be 128. That's just the difference. And your probability is 50%. The really neat thing I think about it is this is like, that's over half the pizzas. And so if over half the pizzas have pepperoni, over half the pizzas will have anchovies, over half the pizzas will have mushrooms. And also it tells you that if you add one more topping, you can actually double the amount of pizzas you can make. If you take away a topping, so no longer offer a topping, you're actually halving the number of pizzas you can make, which is kind of interesting. So here's some questions here, and then this question here is really like what we want to get to is just how do you explain this, creating your own example, very similar to the soup question, where you're using like the same values, 13P3 and 13C3, but you're giving a reason why order would matter versus not mattering.